policy without really saying much about what do we mean by optimality. So in the next 45 minutes or so, I'm going to talk about essentially variations in the parameters of the welfare function, and see what does that do to optimal climate policy. I'm going to focus on social cost of carbon. You can sort of like pull it through an optimization model, but it doesn't add any insight. So I'm just going to focus on social cost of carbon as our indicator for the intensity climate policy. I'm going to start with a simple thesis. Well, it should be clear by now that climate change is a long-term problem, that it's a global problem, and that it's an uncertain problem. And from that it follows that if you do not care about the distant future, or you do not care about faraway lands, or you do not care about remote probabilities, then climate change should not be your concern. Vice versa, if you do care about any of these three, or perhaps all three, then you should be worried about climate change. And that is what I'm going to be talking about. I think in this order. I'm definitely going to start with the future, and I think I'm going to talk about equity and faraway lands, and then I'm going to talk about uncertainty and remote probabilities, though it may well be the other way around. We'll see. I talked about discounting and what the discount rate does to social cost of carbon, but I didn't say much about the structure of the discount rate. A simple way of thinking about what the discount rate should be is to use the so-called Ramsey rule of discount. This is not named after a footballer, but it's named after Professor Frank Ramsey, who taught at Cambridge in the 1920s, died at a very young age. One of his key contributions was to derive this particular rule. It says that the money discount rate, R, is equal to the pure rate of time preference, or the utility discount rate, rho, plus the growth rate of consumption times the curvature of the, I'm going the wrong way as well, times the curvature of the utility function eta. Intuitively, essentially what Ramsey said is that we discount the future for two reasons. First, because we expect to be richer and happier, and that ends up in this term here, which is essentially the growth rate of happiness. And how does discounting work? Essentially, if you're making a savings decision, then you're transferring money from today to the future. Essentially say, I'm going to consume less today, and then in return I'm going to consume more tomorrow or next year. And that is essentially a transfer. That is a transfer from you today to you in the future. And the way to evaluate this is as follows, and this is essentially what this part of the Ramsey rule does, is let's suppose that we have money on this axis, or consumption on this axis, and utility on this axis, and then the red curve is your utility function. And then essentially what you're doing is you give up, say, 1 pound of consumption today, or maybe 100 pounds, and then later on you get it back. Now, if you're giving up 100 pounds today, and then in a future when you are richer, you get 100 pounds back, then that is a bad deal, right? Because you give up this amount of utility now, and in return you get this amount of utility back. I hate these screens. So that would be silly, right? You give up a lot of utility now, and you get very little utility in return. So what this part of the Ramsey rule essentially does is, rather than equate the distance, the horizontal distance, we are equating the vertical distance. So we want our sacrifice today to be equal to our gain in the future, and the discount rate essentially tells you what is the difference between the horizontal distance here and the horizontal distance here, right? Now, it should be intuitive that this depends on two things. One, how fast is your income growing? How fast do you move from your poor self today to a richer self in the future? And the second is, how curved is the utility function? Because if the utility function were linear, then of course it doesn't matter. Then the horizontal distance and the vertical distance would just coincide, right? That's because we would be linear on the 45 degrees line. So that is the first component of the money discount rate. We expect to be richer and therefore happier in the future, so you would be silly to impose misery on yourself today so that you will be happier in the future. And in your case, maybe you're in your third year, you're pretty damn poor now. Hopefully you'll have a job in 6 months' time and you'll be a lot richer, right? So it would be ludicrous for you guys to save now so that in 6 months' time you have more money, right? That would just be a silly thing to do. There is a second reason for discounting the future, and that is the rho, the pure rate of time preference. And that reflects our impatience. If we're talking about pure utility, then it so happens that a lot of people want their stuff and want it now. For the pure sake of things being in the future, they are discounted. So the new series of Games of Thrones will be released in 3 weeks' time, right? And maybe you're getting all excited. If I were to offer you the opportunity to watch it tonight, you would go for that, right? Because you would get all the excitement now, right? The excitement is the same, right? Whether it comes tonight or whether it comes in 3 weeks' time. I mean, the series will be the same. I actually don't know what's going to happen in the first episode. I haven't been paying close attention. But it will be exactly the same, right? Whether you see it tonight or in 3 weeks' time. But still, if I give 100 people the choice, then they would say, I want it tonight. So we are impatient. And that is captured by the pure rate of time preference rho, which is essentially the rate at which we discount future utility. So this is a way of thinking about discount rates and a way of interpreting observed discount rates. It's also a way of having a discussion about the observed, about what the discount rate should be. Consumption, the growth rate of consumption is more or less objectively measured. The curvature of the utility function eta, of course, is a reflection of our preferences, and it will be different for different people, maybe different for different problems, maybe different for different people, for the same person at different points in time. Same is true for your impatience. That's essentially a reflection of your preferences. There's a lot of philosophers, as well as a lot of religious people, who argue, sometimes quite strongly, that it's immoral to discount the future for the pure sake of it being the future. Socrates was probably the first one to argue this. St. Augustine picked this up. Mohammed picked this up. They all say it's immoral to discount the future because it's the future. The latest proponent of this is, of course, Lord Stern. But yeah, that's what people do. And you could also argue, because this is essentially an advice on how high the carbon tax should be, so it is about public policy. And if all the voters in the UK have a positive pure rate of time preference, that is, they're all impatient and they're all discounting the future for the sake of it being the future, it will also be immoral for David Cameron then to say, screw you, I'm going to do it anyway, right? There's also a certain moral obligation on elected governments to respect the will of the people. So here we have an ethical, empirical conundrum. Before I dive into the results, the way I derived or hand-waved the Ramsey rule of discount is from the perspective of a consumer making decisions about how much to save, right? I think that's more intuitive. If the economy is in dynamic equilibrium, then of course the consumption rate of discounts, the rate of return demanded by savers, must equal the marginal return on capital. And of course, in a dynamic equilibrium, the consumer rate of discount is equal to the production rate of discount. You find the same number. And that is actually what Ramsey really did in that thing. So what are the implications for the social cost of carbon? They're actually pretty straightforward. I have 4 graphs, as you may have guessed. I'm going to start with the first one. What we're looking at here is an estimate of the social cost of carbon. That's always on the vertical axis. On the horizontal axis, we put the curvature of the utility function, or the rate of risk aversion. And then in colors we have different rates of pure time preference. And in green the pure rate of time preference is 1, in blue the pure rate of time preference is 2, and in red the pure rate of time preference is 3. And what you see is that the lower the pure rate of time preference, the less you discount the future, the more you care about the future, the more you care about climate change, and the higher the carbon tax that you want to impose, right? The green line is always above the blue line, is always above the red line. So that is the first thing you see. Second thing you see is that as the curvature of the utility function increases, the social cost of carbon comes down. And that is the eta in the Ramsey rule. And essentially this is a redistribution problem. You're transferring money from the poor of today to the rich of the future. And the more curved the utility function is, the less you will be inclined to transfer money to them, and therefore the lower the carbon tax that you want to impose. Right? Unambiguous relationships should be clear. Equity and faraway lands. The impacts of climate change are very different between countries. More specifically, the impact of climate change measured on the vertical here is much greater for poorer countries measured on the horizontal than it is for rich countries. We've been through this and its implications for climate policy and its implications and the reasons why this is. That's what we've been through. Now, the graph that I just showed was measured in dollars. And initially what people used to do is just add up the dollar numbers. So we estimated the impacts in Nigeria, expressed them in dollars. We estimated the impacts in the UK, expressed them in dollars, added them all up, included all the other countries, and said this is the number for the world as a whole. That it turned out to be a fairly unpopular thing to do. Because essentially what you do here is you're adding similar risks up but valuing them differently. And the starkest example is with human health. So health is valued by something that is called the value of statistical life. Essentially means that suppose that the risk of premature death falls by 1 million, falls by 1 in a million, sorry, and you apply that to a population of 1 million, then you would expect to avoid 1 death, or rather 1 statistical death, because you don't know which of these million, who of these million people will be affected, right? Can of course estimate the willingness to pay of people to reduce their risk of premature mortality, and then you would find the willingness to pay, and if you do so you would find that the willingness to pay for avoiding health risks is much greater for richer people than it is for poorer people. And if you would do this exercise for Nigeria, you would find that an average Nigerian, for avoiding the death of an average Nigerian, is worth about $100,000. And for the UK, for the average Brits, it's about $6 or $7 million. Essentially what you're saying is that if through our greenhouse gas emission reduction we avoid the death of a Nigerian, we're going to count it at 100,000, and if we avoid the death of a Brit, we're going to count it at 7 million. So you're saying that Brits are worth 70 times as much as Nigerians. Now, if you try and say that in the UN context, you're in deep trouble. Some people said, well, just take the average. Why don't we just use a different number than the ones that are estimated? That is very strange. Because essentially you measured something and you said, I don't believe my data, I'm going to change it. But there is also a consistency problem there. And that is as follows. Suppose that the Nigerian government is thinking about investing in greenhouse gas emission reduction, and it's thinking about investing in road safety. If it avoids the death of a Nigerian through road safety works, that should, because it's a local problem, that should count as at the Nigerian value of statistical life. That is worth 100,000. If it avoids the death of a Nigerian through climate policy, that is worth the average of 7 million and 100,000, say 3.5 million. So the Nigerian government should put all its money on climate policy. If the UK government faces the same choice, should we invest in road safety or should we invest in greenhouse gas emission reduction, then saving a Brit through greenhouse gas emission reduction would be worth 3.5 million, whereas saving a Brit through road safety works would be worth 7 million. So we should put all our money on road safety. So that may not be the conclusion that you want to draw. And of course you cannot say that somebody dying because of lack of road safety is worth less or worth more than somebody dying because of climate change. Death is death, right? So this is not the way forward. You can't just take empirical numbers and change them. You can't just take national numbers and throw them in a mix and use different numbers for local decisions and national decisions and regional decisions and global decisions. That is just silliness. So the way forward is to use so-called equity weights. Equity weights are essentially a way of correcting for the fact that $1 to a poor woman is not the same as $1 to a rich woman. So if you take your average woman in Nigeria and you threaten to take $1 away from her, that would actually be a big deal. Whereas if you take Melinda Gates and you threaten to take $1 away from her, she would probably not even blink her eyes, right? Now the way to do this formally is through, to account for this formally is through so-called equity weights. So we're interested in a global impact, DW. And that should be measured in dollars or in pounds or in euros or whatever. What we have are the national impacts, D sub C, and they're also measured in dollars. So what do? Essentially we don't want to add dollars, but we want to add the utility equivalent of those dollars. So we multiply things with a marginal utility, U sub C. Then we have things in utility. Then we say, how does a change in national utility contribute to global welfare? That's W sub U. Then we have a problem, right? We started in dollars, we multiplied with something that is measured in utils per dollar, multiplied it with something that is welfare per util. But we want it in dollars, so we need to normalize. The normalization is a bit arbitrary, but received wisdom has that one appropriate way of normalizing this is to slightly slacken the global income constraint. So essentially what we do here is we assume there's a Martian coming along with $1, gives it to the world, and we distribute it among the 7 billion of us in an optimal way. Then welfare would increase ever so slightly, and that is what this measure is. And this then of course is measured in welfare per dollar. So then we have welfare cancelling against welfare, utility against utility, and we're back into dollars. If we assume that the global welfare function is the simple sum of the national utilities, and we assume that utility is a CRRA function, constant rate of relative risk aversion, then the equity weight that you see here in its general form becomes this thing here, where epsilon is again the curvature of the utility function or the rate of risk aversion, and the thing between brackets is essentially global average income over national average income. So what does this do? If we have impact falling on a poor country, then we multiply that impact by the world average over the national average. It's poor countries, so the national average is lower than the world average. So this ratio is greater than 1. We raise it to a positive power, so this ratio stays greater than 1. So we put more emphasis on monetary impacts to poor people. Similarly, if the impact falls in a country that is richer than the global average, then YC is greater than YW, and we apply a weight that is smaller than 1, right? So equity weights emphasize the impact on the poor and de-emphasize the impact on the rich. There's an alternative way of deriving this, or there may be an implication of this. We have this function here. Let's assume that the damages here are impacts on health, to go back to our example. So it is the number of people dying prematurely, that is IC, times their value, VC, right? So this is just a substitution. Now if we assume that the value of statistical life increases with per capita income, and we assume that there is an income elasticity epsilon, then we can say that this national value is the global average value times the income ratio between the national and the global raised to the power of the income elasticity. If we then assume that epsilon equals eta, then yc cancels against yc and yw against yw, and essentially what we've done is we valued everything in the global average. So we took the national number of deaths and we applied the global average value of these. But this only works if the income elasticity equals the rate of risk aversion. There's no reason to assume that that is the case, although people often assume that both of them are equal to 1, but there's no reason for this. There's one thing I've got to say about the equity rates. If the if the eta is 0, that is, we're risk neutral, and consumption or utility is linear in consumption, then of course all these weights are equal to 1. So the older practice of just adding up dollar values across the world essentially assumed risk neutrality, which is an assumption that cannot be supported by any empirical evidence. So what are the implications for social cost of carbon? First, we put more emphasis on the impacts on the poor. The impacts on the poor are greater than the impacts on the rich, so we would expect the impacts to go up and the marginal impacts to go up as well. So if we compare here, say, for a rate of risk aversion of 0.75, I shouldn't touch the screen, I should know that by now, and we compare that to 0.75 here, then we see that indeed the social cost of carbon has gone up. The green line here lies above the green line here, if you look closely. And that is exactly what we would expect. There's another thing that we see happening, and that is that if we increase the rate of risk aversion, then we discount the future harder because we care less about the future rich, or we care more about the current poor, rather. But this relationship actually becomes ambiguous. If the rate of risk aversion gets high enough, then you see that the social cost of carbon starts inching up again. And that is because this parameter here now fulfills two functions. One, it governs the trade-off between our poor self today and our rich self tomorrow, but it also governs the trade-off between rich people today and poor people today. And if rho comes very high, then we start putting more emphasis on the impacts on the poor, and the social cost of carbon increases. There's another thing that happens, and that is that whereas here everything is positive, at least at first sight, here we actually see the social cost of carbon dipping below 0. That is, we want to subsidize fossil fuels rather than tax them. Why is this? Well, we have a high pure rate of time preference, we have a high rate of risk aversion, so we discount the future very hard. At the same time, we put a lot of emphasis on what is going on in poor countries. So what we see here is CO2 fertilization. So in the short run, putting more CO2 in the atmosphere makes plants grow faster, particularly in arid areas. That means that food prices fall, and food prices falling particularly benefits those who spend a large share of their income on food, that is the poor. And we put a lot of emphasis on those short-term benefits that primarily benefit the current poor. And that is why, if you pick these parameters, you want to subsidize CO2 emissions. Okay, I'm going to make it a bit more complicated still. I'm going to introduce uncertainty. Typically what we do if we're confronted with an uncertain problem, we say you don't want to maximize your costs or your welfare, but you want to maximize the expectation of that. Right? And that goes back to Van Neumann and Morgenstern, who show that that is indeed the right thing to do. So the expected damage is essentially the damage, the S in every state of the world, every thing that could possibly happen, times the probability of that state of the world indeed occurring, and you sum over all that, and that's your expectation. That would be a natural thing to do. It would also be a wrong thing to do, because really we're not interested in money, we're interested in utility. So the proper application of micro will tell you is that really what you should be doing is not calculate your expected damages, but stick those damages into your utility function, calculate the expected utility, and then apply the inverse of the utility function to get things back into dollars. This thing here is called the certainty equivalent damage. The difference between the certainty equivalent damage and the expected damage is called the risk premium. This is just definition, there's nothing to understand here. The certainty equivalent damage looks definitely strange, right? We apply a function u inverse and we apply a function u, so that should just cancel against one another. Now you may think that I'm just being particularly pedantic about welfare theory, right? Or you may think, you may wonder what I'm on, right? Now, rather than do the math, just look at these things, let's just look at some numbers, right? Because then the process of what I'm doing with a certainty equivalent damage becomes actually a lot clearer. So we start with an income of 1,000. There's a 50% chance that we lose 10, there's a 50% chance that we lose 20. So the expected damage is 15, right? In the middle between 10 and 20. So that is the expected damage. What is the certainty equivalent? Well, we want to calculate the utility that would occur in the two scenarios. So if you don't lose anything, our utility is 691. If you lose 10, our utility falls to 690. If we lose 20, then our utility falls to 689. I assume a logarithm here. So we take the average of the two is actually 689. Then we apply the inverse of the utility function, so we take the exponent. So 691 is just the log of 1,000, and 984.99 is just the exponent of 689. We take the difference between these two, and we find that the certainty equivalent damage is not 15, but it's 15 pounds and 1 penny. which is a very tiny difference. The risk premium is 1 penny. So if this is the case, you would be correct to say, what are you on? Why are we going through this much more complicated procedure to calculate a number that is almost the same? Well, what happens if these two impacts, 10 and 20, don't fall on somebody with an income of 1,000, but on somebody with an income of 100, right? Then it's 461, 450, 438. The average is 444. Take the exponent of that is 8485. So the certainty equivalent impact is £15 and 50 pence, and the risk premium is 15 pence. It's a still pretty tiny difference, right? What happens if the impact is not 10 with a chance of 50% and 20 with a chance of 50%, but 10 and 98 with a chance of 50%? Well, to somebody on an income of 1,000, right? Here the utility is still 690. Here the utility falls from 689 to 680. A pretty small drop in utility. So the average is 685. We take the exponent of that to find 944, and then we have a certainty equivalent impact of £55, whereas the expected impact is £54. Still, the risk premium is pretty small. But if this fate befalls somebody on an income of 100, and the crucial bit here is of course that they lose 98% of their income, right? Rather than 98, it's 98%. That is the crucial number here. You see that the utility falls very rapidly from 438 to 0.69, which is a much bigger difference because of the nonlinearity of the utility function. So the expectation of utility is 260. Take the exponent 13.4. The certainty equivalent damage goes to 87 pounds, right? So we have a risk premium of 33 pounds. And now we drive a substantial wedge between the expected damage and the certainty equivalent damage. And that is because there is a probability of losing it all, right? And that gets a disproportional weight because of the curvature of the utility function. So here we see the same thing, but now for different scenarios and for different in red and for different probabilities. So here we have a 50% chance of losing £10, and then a 50% chance of losing nothing, £5, £10, and then we increase all the way up to income. And what you see is that the closer we get to a total loss, the bigger the difference between the expected damage and the certainty equivalent damage becomes, right? That's the gap between the two red lines. Something similar happens if we evaluate the scenario of £10 loss versus £98 loss, both relative to an income of 100, where here the probability of losing 98 is 0, and therefore the chance of losing 10 is 1, and then here the probability increases until we're certain again. Of course, if there's no uncertainty, then certainty equivalent damage and expected damage are the same. But in between you see that a large wedge is driven between the expected and the certainty equivalent damage. I think the red line is the more intuitive and the more appropriate here. Essentially what this says is you can just do your standard calculus in expectations in dollars if you're somewhere here, because then the risk premium is basically 0. But if there is a chance that because of climate change we're going to lose something that is very close to our income, that is, there is a chance of a total loss, then we should really take into account the nonlinearity of the utility function. And of course, if the utility function, if it's a simple log, If consumption approaches zero, then of course utility approaches minus infinity. And that explains why this goes up, and it actually goes up exponentially to infinity, even though I did not quite draw that because it's a bit too high, right? So if there is a chance of a total loss, then that should dominate our welfare calculus in a way that would not show up in an expected cost-benefit analysis. We really need to go to the welfare calculation. So that drives this result. So here we look at the social cost of carbon as a function of the pure rate of time preference and the rate of risk aversion, ignoring uncertainty, ignoring equity. Here we introduce uncertainty, but I continue to ignore equity. What you see, first the pure rate of time preference is still the same. So the green line lies above the blue line, lies above the red line. So that hasn't changed. Uncertainty, if you compare this green line to this green line, uncertainty lifts the social cost of carbon because the chances of things going wrong with climate change are greater than the chances of things going very, very well. In other words, the probability densities are all asymmetric and the bad tail is more prominent than the good tail. We see that the social cost of carbon under uncertainty goes up. It's another thing that we see, and namely that the relationship between the social cost of carbon and the rate of risk aversion becomes ambiguous. So if we go from risk neutral to a modest rate of risk aversion, then the discounting effect dominates. We care less about the future. At the same time as the rate of risk aversion increases, we put more emphasis on the remote probabilities, and the social cost of carbon goes up. Right? And the same is true for the blue line, pure rate of time preference of 2%, and the red line, pure rate of time preference of 3%. Now, throwing equity back into the mix, essentially the curves go up a little bit. The main difference between this one and this one is that now the positive impacts of CO2 fertilization are dominated by the risks of things going dramatically wrong in poor countries in the further future. Actually, all the positive impacts disappear from here. If you look at this graph, it is closer to this one than to this one qualitatively. In other words, if the parameterization of this model is correct, then uncertainty is a bigger concern than equity, right? Now, this is the appropriate graph because here we looked at all the three elements. The social cost of carbon here ranges from somewhere very close to zero to greater than 1,000, which is unfortunately the way these things are, right? Depending on your choice of the pure rate of time preference and your choice of the curvature of the utility function, you can essentially defend any value for the social cost of carbon, any intensity for climate policy. That is unfortunately the way it is. It puts people in awkward positions if they want to give policy advice, right? Because essentially the advice is, I mean, I can justify any climate policy by just picking the right numbers. which gives leeway for all sorts of manipulation and dishonest advice. It's perhaps not what we want to do. So really we should do it the other way around and sort of like pick these parameters and from there derive our conclusions. I talked a little bit about this before. There's two ways to guide this: try and measure them and take some efforts of what people say. Problems there is that these things are very hard to measure with any sort of accuracy. And you can sort of derive my discount rate by looking at my savings behavior or looking how much I pay for my mortgage. And then you know my personal time preference. But of course that's not what we're interested in. We're here interested in the social time preference. And there is no reason to say that the way I make decisions about savings and investments should be the same as I think that society should make decisions about savings and investments, right? So there's problems there. You can also look at thought leaders. I list 3 here about what they would say about these things. But then of course you're back in the paternalistic way of thinking. Why is Lady Gaga's opinion more important than mine, right? Crucial thing here to keep in mind is that if you make a choice about these parameters, then it doesn't just affect climate policy. Climate policy is not the only policy where we're interested in the future, where we're interested in distributional consequences, where we're interested in uncertain outcomes. And something that should be close to your hearts is education, right? I mean, as soon as you introduce a public policy, a public subsidy for education, as we do in this country, and I think rightfully so, you're investing in the future, right? You're not educating people for now, but you're educating them for later. The returns are uncertain, right? And of course, these investments disproportionately benefit those who would otherwise not be able to pay for their education, that is, the relatively poor. So in that sense, investments in education are like investments in climate change, and you can't say, well, I'm going to use one pure rate of time preference for climate change and another one for education. That would just be very, very strange, or a different rate of risk aversion, or a different rate of inequity aversion. So that is something to keep in mind, that you're not just free to pick these parameters and therewith your optimal climate policy. Right? Okay, that's all I have to say for today. I see you guys